Hey everyone, this is Alice. We're going to do one more example with simulation-based inference. So the question is, was Paul the octopus really an oracle? And he was an octopus who supposedly predicted the results of international soccer matches. And the way the predictions were done is the following. He would be presented with two boxes very similar to each other, and each of them had the flag of two different countries, and then there was food in both of them, and so the box that he ate from was taken as his prediction for who would win the soccer match. So his success rate overall was 12 out of 14. And he got a lot of press on this because 12 out of 14 seems like a pretty good rate. So we're going to go ahead and test it using hypothesis testing. Okay, so in class we talked about the null and the alternate hypotheses. And so the null hypothesis is Paul is really just an ordinary octopus. He does not have the ability to predict soccer wins. And the ratio of the number of games predicted correctly to the total number of attempts should be 0.5. That's what we're assuming. And the alternate hypothesis is that he is an oracle. He does have the ability to predict soccer wins. And so his prediction rate would be greater than 0.5. And as we talked about in class, we say it's greater because in the sample it shows that it's greater. 12 out of 14 is definitely bigger than 7 out of 14, but is that significant enough evidence? So let's take a look at letter B. Describe in detail a method to conduct a physical simulation of the situation. There are different ways to do this, but the one that I thought of is that you could begin with 14 fair coins, and each coin toss represents a prediction attempt. And so we can designate a head as a correct prediction. It could have been a tail. It doesn't matter. And so you can toss 14 coins at once and count and record the number of heads. And tossing all 14 coins at once would be considered one trial. Or you could toss one coin 14 times or 7 coins twice. It doesn't matter. So just as long as you have some kind of simulation for each prediction attempt. So after you repeat this many, many times, they're going to count the number of trials whose outcome was 12 heads or more. So the ratio of this number to the total number of trials is a p-value. So if we conducted 1,000 trials of this simulation and created a dot plot of the results, describe the distribution you would expect, and we have seen in the past that the distribution of sampling has converged to a normal distribution. All right, let's go ahead and take a look at the applet. Variable name, we can say Paul's predictions. And we have two different categories. The correct predictions, where in the sample there were 12 of them, and the incorrect, where there were 2. So we'll begin analysis and compare the correct to incorrect predictions, and let's go ahead and do a simulate sample count category to indicate as success the ones that are correct. Hypothesized value is the true proportion, which is 0.5, and let's go ahead and start with 1. Okay, so here remember the total number of attempts was 14. So for the first trial, it looks like there were 7 out of 14 correct, which is what you would expect. Ooh, but here we have some variability, and this time he got 5 correct, and then 8, and then 6, and then 5, and he hasn't gotten 12 yet. So let's see if we do, where are we, 41? Let's see if we get to 12. Not yet. So it already looks like it's very unlikely. I'm going to speed this up and add 1,000. And as we assumed, it would center around 7 out of 14. Let's do it again and again, and you can see it is starting to look more and more like a normal distribution. So we're going to count the number of dots that are greater than or equal to 12. So let's count them. There are not that many, only 29 out of 5,074. And if we look at the percent, it's only 0.6%. So if we assume that the probability that he get a prediction correct is 0.5, then it looks very unlikely that he could have gotten 12 out of 14 by random chance alone. So in this test, the p-value was about 0.006, meaning that it was very highly unlikely that Paul correctly predicted 12 or more of the games by random chance alone. Therefore, we reject the null hypothesis that he does not have the ability to predict and accept the alternate hypothesis that he is an oracle. And this is probably why he became so famous and has his own Wikipedia page, is because it seemed very unlikely that he could get 12 out of 14 correct by random chance alone. Yes, definitely the p-value of 0.006 is very statistically significant and shows that it was very unlikely that he was able to predict 12 out of 14 games by random chance alone. So again, we reject the null hypothesis because the p-value is very low, 0.006. Usually 0.05 is an acceptable significance level, and this was 10 times less than that. Very unlikely this could have happened by chance. So hopefully this makes sense, and let me know if you have any questions, and I'll see you tomorrow. Bye.